right. So good afternoon. So let's get started. Why should you care about hashing in the class groups of imaginary quadratic fields? What are even class groups of imaginary quadratic fields? Maybe some of you are not familiar with it. Don't get intimidated. In a few minutes, you will figure it out. We will figure it out together. So the reason why we are here is because such a cryptographic primitive, namely hash functions to class groups, have a lot of applications. Verifiable delay functions, zero-knowledge proofs, and timed commitments. More broadly, they will have a lot of applications in time-based cryptography. If we zoom out a little bit, it's often quite tricky to map messages into cryptographic groups. If you just think about our beloved RSA signatures or encryption schemes, there are already existing standards that define such a function. Or if you think about BLS signatures, this is also what happens there, that we have a message, bit string, byte string, that we want to map into an elliptic curve. And in this talk, what we are interested in is how to map messages, bit strings, byte strings, into class groups of imaginary quadratic fields. But what are class groups? You can think of at a very high level as they are a sibling of an RSA group. Namely, they form a group of unknown order. So nobody knows the group order in case of a class group, but for an RSA group, you only don't know the order of the group if you don't know the factorization of the modulus. So if we want to set up such an RSA group, typically what we do is we trust a certain person to set up, to generate the primes, and we trust this trusted party to delete the prime factors. We can distribute this trust using some multi-party computation protocols. On the other hand, for class groups, we can set up a group of unknown order in a way that we don't need any trusted party or an MPC protocol, because we can just generate a random prime number, and then nobody will know the order of the group. So that's cool because it has a lot of cryptographic application. What are the group elements of a class group? They are binary quadratic forms. We are going to see it in a second. The downside of this group of unknown order constructions is that they have quite large group sizes. So because the reason is that there are sub-exponential algorithms to factor an integer, and there also exist sub-exponential algorithms to compute the class group's order. So, and we know how to compute efficiently the group operation in case of an RSA group, Karatsuba multiplication algorithm, and on the other hand, for class groups, we know how to compute the group operation using Shank's algorithm. Okay, so what did we do in this paper? We were studying broken hash functions into class groups, so they were used in open source libraries. Even though these constructions were not designed with cryptographic applications in mind, we think that these are valuable lessons for the hash function designer. And then in the second part of the paper, we describe two families of secure hash functions into class groups. And in the last part of the paper, we implement these techniques and evaluate their performance. And here's a link to the quick and dirty Python proof of concept code. Yeah, feel free to check it out. So in the next 5 minutes or so, I will give you a high-level introduction to class groups and class group elements. So don't worry if you don't know yet how a class group looks like. Then I will describe these broken hash functions into class groups. Then I will describe the secure hash functions into class groups, and perhaps most importantly for us researchers, I will conclude with some, I think, interesting research questions. Okay, so what is a class group of imaginary quadratic fields? The elements of a class group are binary quadratic forms. And what is a binary quadratic form? It's a function in two variables. So it looks like ax squared plus bxy plus c times y squared. And we can represent such binary quadratic forms as a triplets of integers abc. The most important thing of a form is its discriminant. You might have heard the word discriminant in elementary school or kindergarten. So the discriminant of a form is defined as b squared minus 4ac. And what we do in class group crypto is that we fix a prime delta. Let's say, just as a toy example, let's fix delta to be minus 23 because we love LeBron James and Michael Jordan. So the CL minus 23, it's a very short, very small class group. It only has 3 elements. And these are the binary quadratic forms that are in this class group. And it's easy to see that the coefficient a and b must be smaller than the square root of delta divided by 3. So there's an upper bound for a and b if they are in the class group. So typically we represent class group elements as a and b. There's no need for c once we fix the discriminant delta. But there's even more tricks how we can compress group elements using some techniques described in Dobson, Galbraith, and Smith 21. Okay, so we know that there's a group structure on CL delta, and this is a classical result due to Gauss. So if we have 2 binary quadratic forms, we can compose them and we will end up with a 3rd binary quadratic form. Another important theorem is that we have a closed formula for the class group order. This is the famous class number formula of Dirichlet. Even though this is a closed formula, it seems that it doesn't help us to compute in polynomial time the order of the class group. What's important here is that the order of the class group is proportional to the square root of delta. And as of 2025, April 28, to the best of our knowledge, there is no polynomial time algorithm to compute the order of CL delta. For us cryptographers, this is good news, but for mathematicians, they are not that happy about it. Okay, so here's our toy example, CL minus 23. These are the class group, the binary quadratic forms that are in the class group. And you could say, hey, wait a minute. It seems that this is not all the binary quadratic forms that are in the class group, right? Because G138 is also a binary quadratic form, and it should be in the class group, right? Because if we do the very simple math, the discriminant of this G is 3 squared, 9, minus 4 times 8, which is minus 23. So this G should be in the class group. But what we see is that this G is not enlisted above there. So why is that the case? Because we can obtain G from F by a linear transformation of the variables. So if we write F as, instead of writing X, we just substitute it as X plus Y. So we just linearly transform the variable X, and then we do this really silly computation. Then it's easy to see that we will end up with the form G. So what we do in class group crypto is that we think of binary quadratic forms as equivalent if we can obtain from one form, if we can obtain using a linear transformation from one form another one. And the representative of this equivalence class, we call it as a reduced binary quadratic form. Intuitively, it means that the coefficients of the form is small. So CL delta, the class group of imaginary quadratic fields, is a set of reduced binary quadratic forms. If we zoom out, it is kind of analogous to the RSA group, integers, multiplicative group of integers mod n. So let's say, just as a toy example, modulo 8, 3 and 11 are the same. So whenever we want to compute, we think of 11, we can compute just using 3. And in fact, computationally, it's more efficient if we do all the computations with 3. This is just a toy example. Okay, so what do we want from a hash function into a class group of imaginary quadratic fields? Okay, so here's just for your convenience another toy example of a small class group. And so what we want is the function must be deterministic, efficient. So hopefully such a hash function will be used by many downstream cryptographic applications, such as signature schemes, encryption schemes, verifiable delay functions, and many more applications. So the hash function must be as efficient as possible. It must be collision resistance. I assume that you all know these classical notions, but what's really important is that what we want is that the hash function must be uniformly distributed. So it's called, such a hash function is called universal hash function, and it means that the codomain of H is uniform. Put differently, it means that every binary quadratic form has an equal probability, has an equal chance of being the image of an input. So yeah. This is our desiderata. Okay, so now let's see some negative examples, so how not to hash into class groups. But before that, let's little bit zoom into the structure of a class group. So here's a beautiful 9-digit prime number, and it's quite a large class group with thousands of binary quadratic forms in it. I'm not going to enlist all the binary quadratic forms, but now let's just look at the distribution of the coefficients A of all these binary quadratic forms in this group, and let's have a look at the distribution of coefficient B that are also in this class group. And what we see is this is the distribution, it's a histogram of all the coefficients A that are in the class group, and what we see is that this is not a uniform distribution. And we know how to characterize this distribution. It's a classical result. You can have a look at it in the paper. And similarly, if we look at the histogram of the coefficients B, it's also not a uniform distribution. Note that the y-axis in case of the coefficient B is logarithmic. So what's important here is that neither of these two distributions are uniform. Right. So, and we were not able to fully characterize the distribution of coefficients B. We had some partial results, and our conjecture is that this is the distribution that it follows. Just to zoom out, if you think of elliptic curves over a finite field, and we enlist all the rational points over Fp, then the distribution of coefficient of the coordinates x it will be uniform as p goes to infinity. So if we enlist all the rational points of a curve, then both x coordinates and y coordinates will converge to uniform distribution. But this is not the case for class groups. So at a high level, it kind of says that class groups are not quite generic group in some sense. Okay, so how not to hash into class groups? So even Arnold says that don't do this at home. So a natural idea might be that we sample a random coefficient B and then try to see what's the corresponding coefficient A, and we output this as the hash output. And in fact, this strategy was used by a cryptocurrency wallet in an open source implementation. So this is a bad strategy because we have just seen that the coefficient B in the class group is not uniformly distributed. So the hash output will be also non-uniform. And remember that we want that the codomain should be uniformly distributed. Similarly, it's a bad idea to generate a random A, a uniformly random A in this interval, and then finding the corresponding coefficient B, and output this as the hash output. Again, this is not a good strategy because in the class group, as we have seen 2 slides before, the coefficient A is non-uniform. Another straightforward but trivially broken construction may be that we take the byte string, the message M, and we raise it to we take a publicly known form and we just output F to the M. But typically in many applications, what we want is that the discrete logarithm of the hash output should be unknown for any public parameter. So these are not good strategies. One strategy that was used in SageMath is that they generated a random form and they reduced it. What's the problem with this strategy? So we just generate a random form in a square. We generate a random A, random B. We generate a random form, reduce it. It's completely insecure because now the codomain has a power law distribution. So know that on the right-hand side, both axes are logarithmic. So if the codomain is this skewed, then we show in the paper that certain cryptographic applications, verifiable delay functions, are completely broken. So what we see on the right-hand side is that binary quadratic forms with small coefficients have much higher probability to end up being the image of the hash function. So a VDF evaluator could just pre-compute all those VDF outputs for those small coefficient binary quadratic forms. Okay, so how to hash into class groups? The first secure construction is that we have imagined that it's basically, if you know Reingold BRF, that's kind of really similar in spirit to this construction. So what we have is we have D binary quadratic forms. We pre-compute them. These are denoted as Fi. You can think of this as some basis, kind of, basis quadratic forms. And we take the input x, we hash it into an integer from 0 to x. We assume that we can hash into the integers. And once we have this set of random bits, we can take the dot product of the random bits with these bases. And then basically now a Reingold PRF. And this is what we output. And it's easy to show that this is secure. And heuristically speaking, it also produces a uniform output in the codomain. Okay, the second family of constructions, so this original construction was described in Veselovsky's VDF paper, Efficient Verifiable Delay Function paper, 2018 or 19, Eurocrypt. And the strategy here is, let's assume that we can hash into the prime numbers. So we have a certain interval and we can hash into the prime numbers in that interval. What we do is we take a random prime from this interval, and now, given this prime number, we can compute the corresponding coefficient b, which can be obtained as the square root of delta mod p. And there are two forms, either pb or p minus b. And we output one of these forms. What's the downside of this? This is also a secure construction. What's the downside? The downside of this construction of Veselovsky's is that it only outputs prime forms. We call a form prime form if the first coefficient, the A coefficient, is a prime. So, but this is just a tiny fraction of the whole class group. So what we do in the paper, so this is not a surjective hash function. And what we want to do is we want a hash function that has the codomain of the entire class group. And in fact, in the paper, we show how to make this original construction of Veselovsky to be surjective. We also evaluate the performance of these hash functions. What we find is that our improved Veselovsky's construction is the most performant for cryptographically relevant parameters. So this is the green line on both sides. Okay, so where do we go from here? More efficient hash to class group functions. If you know any, or if you have any idea, let me know. I think it would be cool to have more constructions. Yeah, hash to prime functions, that also seems to me like an underexplored area, especially constant time hash to prime functions. I think what's also interesting is the efficiency in an arithmetic circuit computation model. So class group crypto the deployment of class group crypto is a little bit hindered by the fact that we need these 1,000 bits large groups. And so for resource-constrained verifiers, like in a blockchain or smart contract, typically you don't want to do this large arithmetic. So what you want to do is you could outsource the computation of the class group arithmetic. Somebody does it off-chain, and on-chain you would just prove the correctness of this class group operation. I'm not aware of any implementation of class group arithmetic in Noir, Circom, or Cairo. Constant time hash to class group functions, we didn't bother for our implementation to be constant time. That would be cool if somebody would do that. More applications of such a fundamental cryptographic primitive. That would be also nice. If you have any idea, let me know. And yeah, more performant class group crypto libraries are needed. Yeah. And so class group crypto implemented for ZKP circuits, that would unlock a lot of applications. And yeah, it would be nice if somebody would implement class group arithmetic in Noir, Cairo, Circom. Okay, so if in your firm there's a protocol that you need to use a random binary quadratic form, then you should use any of these hash functions. In particular, if you use VDF, a verifiable delay function, then most likely you do want to use a class group-based VDF because it doesn't need a trusted setup. Then in that case, you also most certainly need such a hash function. And yeah, there's lots of room for efficiency improvement, in particular for resource-constrained applications. Yeah, so the world needs more class group crypto implementation. Please help. All right, so with that, thank you very much, and let me know if you have any questions.
Good afternoon, everyone. My name is Jiayi Ai, and today my topic is sequential indifferentiability of 7-rung MISTY structures. Block ciphers typically follow two types of structures, namely Festool networks and substitution permutation networks. Recent developments in block ciphers have pushed revisiting non-classical structures. One of them is the MISTY network. Compared to the Festool structure, it is quicker and more resistant to linear and differential cryptanalysis. The MISTY structure comes with two flavors, which is now known as MISTY L and MISTY R. Both define two n-base permutations upon n-base round permutations P. Now, let's start by recalling the structure of the MISTY network. So, this is a 7-rung MISTY network, and each wire is n bits. We use UI to represent the intermediate values I equals 1 to 9. So each value UI is n bits long and satisfy this relationship here. We will call the PI here random permutation. The PI is round permutation and I equals 1 to 7. The MISTY network is a 2n-base permutation with input U1, U2, and output U8, U9. We assume that the permutations are all independent random permutations. The question is, to what extent is such a network like a random permutation? Let's look at the classic indistinguishability experiment. In this experiment, we have a distinguisher D, and it is interacting with one of the two words. As you can see, the real word and the ideal word. We assume the distinguisher is information theoretic distinguisher, and it has unbounded computational power. It just has a limited number of queries to its oracles. In the real world, it interacts with MISTY network, and in ideal world, it interacts with a random permutation P. In both words, it has two set queries to the oracle, so it can query backwards. And here, the advantage is delta is defined as the gap of the probability of the distinguisher D outputs 1 in real world and ideal world. But in today's talk, we will use a stronger notion. We call it indifferentiability. Block Cepher's traditional security definition is that it cannot be distinguished from a secret random permutation. Since 25, several scholarly articles have suggested that the concept of indifferentiability from ideal ciphers serves as a significantly more robust criterion for assessing the effectiveness of ideal function-based block ciphers. In this case, we give the distinguisher D access to the wrong permutation Pi. However, in the ideal world, there is no wrong permutations. So we will have to construct a simulator. Here, simulator S try to behave like the wrong permutations. Now the distinguisher cannot distinguish between the two words. And we require the simulator to be efficient and it has the oracle access to P. So our goal is to construct a simulator. Also, we need is the advantage is delta is in the two word is negligible. This property implies that the cipher MISTY inherits all ideal cipher properties defined by single-stage games, including security against various forms of related key and chosen key attacks. But in today's talk, we will give another notion, the notion of sequential indifferentiability introduced by Mendel is a weakened variant of full indifferentiability of manner, tailored to a class of restricted distinguishers named sequential distinguishers. For concreteness of a formalism, concentrates on block ciphers. Consider the block cipher construction C, here C, built upon several random permutations P, a distinguisher D with oracle access to both the cipher C and the underlying permutations P, is trying to distinguish a C from the random invertible permutation pi. And if D proceeds through the following steps in a strict order, it can be considered as sequential. First, it queries the underlying permutation P in arbitrary, and second, it queries the cipher C in arbitrary, and last, it outputs the result and cannot query P again in this phase. This order of queries is illustrated by the numbers in the feature as 1, 2, 3. We remark that the MISTY structures have never been analyzed with respect to weaker indifferentiability nor the correlation intractability, since MISTY structure, as you can see, it transforms an n-base permutation to a 2n-base permutation. So positive results may shed more light on domain extension of random permutations. We bridge this gap and investigate sequential indifferentiability of MISTY structures that use independent n-based random permutations in each run. For such MISTY structure, we first exhibit an attack, breaking both sequential indifferentiability and correlation intractability of 5 runs. We then prove that 7 runs achieve sequential indifferentiability, and the 7-run MISTY thus also achieves correlation intractability with concrete security comparable with 6-run Festo and 4-run single key even Mosso scheme. And due to the time constraints, we will focus on the proof of the differentiability of 7-run MISTY structure. Now, our first task is to construct a simulator. And the simulator here maintains an internal table pi that establishes a mapping of entries delta w to values w prime for each I equals 1 to 7, initially undefined for all entries. And the simulator provides the distinguisher D with an interface named query I delta W, which enables querying for the internal permutations where I equals 1 to 7 represents the permutation, and delta equals plus or minus denotes whether the query is direct or inverse, and W, which is Amber's law, indicates the value being queried. And the design of our simulator closely follows existing simulators for 6-run Festo and 4-run single key even Mosso. We detect chains in the middle third and fourth runs, and adapt chains in the first and last 2 runs. The main difference is that due to the slower diffusion in MISTY, our simulator needs an additional run, the 5th run, to avoid certain collisions. It thus needs 7 runs in total. Upon receipt of a query, the simulator searches table pi to ascertain whether the corresponding answer is already defined. If so, the simulator outputs the answer and remains in a state of readiness for the next query. Otherwise, it queries the explicit randomness source W prime to have a random answer, and defines. The simulator then runs a chain compilation mechanism to ensure consistency with the random invertible permutation pi after selecting the answer W prime at random and before returning it to a distinguisher. Namely, in the scenario where the distinguisher initiates query with I being either 3 or 4, the simulator completes all newly created chains. For instance, that the distinguisher queries query 3 plus U3, where U3 has not been previously queried. The simulator then queries P for the random response V3. Then for each U4, the simulator evaluates the MISTY construction forward, letting V4 defines pi4 plus U4, and U5 is defined with 3 exclusive U4, and V5 is defined query 5 plus U5, then we get U6 is defined with 4 exclusive U4, U7 is defined without exclusive U6, and backward letting U3 is defined by 3 minus V3. V2 is defined U3 exclusive U4. U2 is defined query 2 minus V2. V1 is defined U2 exclusive U3. U1 is defined query 1 minus V1, and U8, U9 is defined pi plus U1, U2. Then we can get the V6 and V7 and 2 corresponding input and output values for the 6th permutation, and for the 7th permutation are defined. In order to ensure consistency of the simulated MISTY construction with pi, the simulator then adapts, rather than citing randomly, table pi6 and pi7. And this is an instance of our simulator. Then we use 3 systems for the proof as shown in the figure. In detail, we denote S the simulator with oracle access to the random invertible permutation pi, and using random permutations P as source of randomness, and let the system 1 pi x be the system capturing the ideal or simulated world where pi is a random invertible permutation and P are 7 independent random permutations. And all sources of randomnesses in system 1 are captured by the pi P, and let system 3 MISTY P be the real world. All the randomness of system 3 is captured by P. And now we have 2 systems in the left and in the right, and we need a new system. So we introduce the system 2 as an intermediate system, which is derived from the system 1. By substituting the left oracle pi with a MISTY instance that queries the simulator to evaluate, and the rest remains unchanged. So all the randomness of system 2 is captured by pi P2. Then we characterize the distance from system 1 to system 2, as well as the distance from system 2 to system 3. So we can know that the real world is indistinguishable from the ideal world now, and we prove it. Okay, that's all. Thank you.